Hello humans! Welcome! Today we're going to examine how carbon dioxide in the atmosphere can affect the pH of water, how that impacts the weathering of rocks, and lastly, how CO2 in the atmosphere can impact organisms in the ocean, and ultimately the overall health of our planet. Okay, so we're going to start with these two vials. These vials contain tap water, and the water in these vials has, well, they're capped now, but they have already equilibrated with carbon dioxide in the atmosphere. So we know how much CO2 is contained in the atmosphere at present. So from that you can calculate, from theory, what the pH of the water is. But what we're going to do is modify the atmosphere or the CO2 content of the second vial such that it has more dissolved CO2, and we're going to determine how that impacts the pH. Alright, so vial number 1 is in equilibrium with CO2 in the atmosphere. For vial number 2, we're going to add dry ice. Maybe you can see it better with the blue background. So dry ice is pure carbon dioxide frozen. Okay, so this is just solid CO2. So we're going to add that to vial 2. Now carbon dioxide is interesting because it does not go from, the ice doesn't melt. It doesn't go from a solid to a liquid and then a gas. It goes directly from a solid to a gas. So it undergoes a process known as sublimation. Now hopefully you can see in the vial here that those pieces of dry ice are subliming, so they're releasing carbon dioxide into the water. That carbon dioxide is then essentially purging the air out of this vial, and we can assume that the atmosphere within this vial is 100% carbon dioxide, which means it would have a partial pressure of 1. So we're going to let that bubble for a few seconds here. And so I suspect that it doesn't take long for the water in vial 2 to equilibrate with the carbon dioxide. Alright, so what we're going to do now is measure the pH of the water in vial 1 and vial 2 and compare them. So we're just going to use pH indicator paper, which gives us good enough precision for this demonstration. So there's a couple ways you can do this. We could just dip this directly into the solution. That's not really a good laboratory practice because we would potentially contaminate this sample with whatever chemicals are contained within the indicator paper. Probably not a big deal, but the better way to do this would be to remove a small amount of water from the vial and add it to the indicator paper. Okay, so we can use a plastic pipette. And you don't need a lot. 1, maybe 2 drops at the most is all you need. And then if you remove some of the excess water and let that sit, it'll give us our value. Okay, I'll do it for the second vial here as well. Okay, remove the excess water, lay it down. Alright, let's have a look. So hopefully the colors are coming out okay here and that we're in focus. I'm actually going to position these. Okay, let's see. Let's do the one on the left. To me that looks like it's a pH of about 5. And the pH of vial 2, which has been bubbled with carbon dioxide looks like it has a pH closer to 4. Okay, so there's a little bit of wiggle room here. These indicators clearly only have a precision of about half of a pH unit. But what we can clearly see is that when water is exposed to additional carbon dioxide, the pH drops substantially. Okay, so what we can conclude from that is that once CO2 absorbs into water, it reacts with water to form carbonic acid, which is why we see a decrease in the pH. Oftentimes, the generation of carbonic acid, particularly in soils and sediments, will enhance the weathering of rocks. And when that occurs, we can get the generation of essential elements, such as calcium, enriched in solutions. Okay, so what we have here is just a vial containing a few milliliters of a calcium solution. Okay, and for the purpose of this experiment, we can presume that this is representative of river water. Okay, and so this river water is going to flow into our model ocean. Okay, so the pH of this solution is a bit higher and it contains a lot of carbonate ions. Okay, and calcium and carbonate are two ions that are essential for calcifying organisms in marine environments. They precipitate calcium carbonate to form their skeletal structures. And these include a whole range of organisms, such as shellfish, even phytoplankton, coccolith phytoplankton, which are absolutely vital for the production of oxygen for our atmosphere. Okay, so we can see from both of these solutions, they are transparent, okay, and they're clear. So whatever's in there is fully dissolved. When we combine them, you should see a lovely white precipitate in the model seawater. Okay, so the solution is now cloudy. It's opaque because there is a precipitate in there now. All right, so let's check the pH of that, see what we got. Nice blue color. Let's have a look at our color key to see what we got. And that looks like it's at least a pH of 10, though it could be higher because we're at the top of our scale. Okay, so the point here is that the pH is more basic or alkaline rather than acidic, and we have a stable precipitate of calcium carbonate in that solution, which we can pretend are our lovely calcifying marine organisms. So what do you think happens if we increase the amount of carbon dioxide? You can presume, for example, the amount of CO2 in the atmosphere increases. That'll be absorbed by the ocean, and based on the previous demonstration, that should result in a decrease in the pH. Okay, so same process as before. The frozen solid CO2 is subliming, so it's just releasing CO2 into the water. The headspace above the water should be fully comprised of carbon dioxide. It should displace whatever air was in there. So this demonstration is a bit on the extreme in that we have an atmosphere composed of 100% carbon dioxide, but you can still understand the general concepts behind some of the risks that we face as we continue to increase the concentration of carbon dioxide in our atmosphere. As we do so, more CO2 will be absorbed by the oceans. So our CO2 is about finished here. I think what actually happens is that over time, these pieces of dry ice actually begin to freeze water, to form water ice around them. So just get rid of that so it becomes a bit more clear. But what I think we can start to see is that our precipitate is just about gone. So if we wipe this off to remove the condensation on the outside of the tube, we no longer have that opaque white precipitate. Okay, our solution is now transparent. Okay, you can see my finger on the back side. It's transparent and clear. So the calcium carbonate has dissolved. Get rid of our CO2 there. So this was a bit of an extreme example by adding so much CO2, but I think conceptually it becomes quite clear what the risks are for the biosphere of not just the ocean but our entire planet if CO2 concentrations increase to a certain point, which lowers the pH of the ocean. And just to verify what's happened here, let's check the pH. Okay, so that's sort of at the high end of this indicator. Let's look at a different one. Okay. Ah, yes. So the pH is certainly something around 6.5, somewhere around 6.5 to 7. Just to compare that with before adding CO2. So the blue indicator on the right is indicative of a pH of 10. After adding the carbon dioxide, the pH has dropped down to somewhere around 6.5 to 7. All right, well, you might as well have a little fun with the leftover dry ice. So the beaker on the right has cold water. The one on the left has hot water, which I'm going to add this slowly. All right, cheers.